In section 3.1, we are looking at an introduction to determinants in higher dimensions. So to warm ourselves up here, let's start by recalling the definition of the determinant of a 2x2 matrix. So if we have some matrix A here, we recall that the determinant of A is determined using crisscross multiplication. So we have this entry A sub 1, 1 multiplied by entry A sub 2, 2 minus entry A sub 1, 2 times A sub 2, 1. And we could take this one step further and say that if this determinant does not equal 0, then A is invertible or singular. So let's look at a quick example here. We're asked to find the determinant of matrix A, where A is defined as the matrix 7, 5, 1, 2. And so plugging these entries into our formula, we have the determinant of A is 7 multiplied by negative 2, which is minus 14, minus 5 times 1, which is 5, leaving us with a determinant of negative 19. And again, we can note here that since this determinant does not equal 0, the matrix will be invertible, or is invertible, or singular. So this is all well and good, but what about if we're given a matrix that's larger than a 2x2? And that's what we're going to explore today, is finding the determinant of larger matrices. So for an n by n matrix A, such that n is greater than or equal to 2, the determinant of matrix A is the sum of the n terms of the following form. So we have plus or minus entry A sub 1j multiplied by the determinant of the matrix A sub 1j. We could alternatively write this as plus or minus entry A sub 1j. And it almost looks like the absolute value of the matrix A sub 1j. So that represents the determinant. And this is such that A sub 1j represents the entry of A in the first row, jth column. We also want to make a little love note here to ourselves that these entries are alternating. And so I'll leave you in suspension until we talk about cofactor expansion to see where these alternating terms come from. And then last but not least, we have the determinant of A sub 1j, and we want to make a note here to ourselves that this A sub 1j is a submatrix determined by eliminating the first row and jth column. And so we call this our recursive definition for finding the determinant of a matrix, or an n by n matrix, where n is greater than or equal to 2. So we want to make a little love note here to ourselves that to generalize the definition of the determinant of a larger matrix, we use the 2x2 determinants to rewrite this larger matrix. So to help us understand this process, let's look at an arbitrary illustration here. And we're given a 3x3 matrix A. So using that recursive definition, we recall that the determinant is the sum of the 3 terms of the form. And the reason it's 3 terms is because matrix A is 3x3. And that form is plus or minus the entry in the first row, jth column, multiplied by the determinant of the submatrix A sub 1j. So we are going to need to determine the submatrix for each entry in row 1. So here we go. Looking at the first matrix, we have the first entry in the first row, first column. And to find that submatrix A sub 1, 1, we eliminate the adjacent row and column. Moving to, so actually before we do that, we can actually see there's your little 2x2 submatrix. This is A sub 1, 1. And we do the same thing for our next entry. So this is the entry in the first row, second column. To find the submatrix A sub 1, 2, we eliminate the adjacent row, adjacent column. And we'll do the same thing here with the entry in the first row, third column. To find the submatrix, we eliminate the adjacent row and column. So this is leaving us with the entry in the first row, first column, multiplied by the determinant of the submatrix A sub 1, 1, minus the entry in the first row, second column, multiplied by the determinant of the submatrix A sub 1, 2, plus the entry in the first row, third column, multiplied by the determinant of the entry in the first row, third column. So if you've seen Calculus 3 or vector analysis before, you're recognizing this as the cross product. So let's continue. Right, so now that we have our individual submatrices, we can actually perform our computation. So we can rewrite this. The submatrix A sub 1, 1 is the 2 by 2 matrix A sub 2, 2, A sub 2, 3, A sub 3, 2, A sub 3, 3. And then we're subtracting the product of the entry in the first row, second column, multiplied by the determinant of the submatrix A sub 1, 2. So I have the 2 by 2 matrix A sub 2, 1, A sub 2, 3, A sub 3, 1, A sub 3, 3. Oops. And last but not least, this is plus the product of the entry in the first row, third column, multiplied by the determinant of the 2 by 2 matrix A sub 2, 1, A sub 2, 2, A sub 3, 1, A sub 3, 2. And so this is the determinant of the 3 by 3 matrix A. And so to find the exact value here, we would simply need to compute the determinant of the 2 by 2 matrices in each case. And that's the whole goal with our higher dimension, finding the determinant of a n by n matrix where n is greater than or equal to 2. We're always trying to reduce it down to that known 2 by 2 matrix. So quickly summarizing our observations here, our recursive definition for the determinant of a higher dimension matrix. So we let A be some n by n invertible matrix, and we have that the determinant of A is determined as follows. So you have the determinant of A is equal to the entry in the first row, first column, multiplied by the determinant of the submatrix A sub 1, 1, minus the entry in the first row, second column, multiplied by the determinant of the submatrix in the first row, second column, plus, and we continue in this manner all the way to the nth term. So this is negative 1 raised to the n plus 1. So that's where that alternating factor is coming from, multiplied by the entry in the first row, nth column, times the determinant of the submatrix in the first row, nth column. And we can write this in our summation notation in our compact form. So you have the sum from j is 1 to n of negative 1 raised to the j plus 1 multiplied by the entry in the first row, jth column, multiplied by the determinant of the submatrix in the first row, jth column. So this is our generalized definition or recurrence definition for a matrix in higher dimensions, or for an n by n matrix where n is greater than or equal to 2.